Welcome. Today we'll talk about transformations and what you can do when your data are violating the assumptions of the model you wish to use. So first of all, let's think how we detect any kind of deviation that might exist from our assumptions. So let's take our two key assumptions that are common with most parametric tests, the assumptions of normality and the assumptions of having homogeneous variance across your groups. So for normality, we can go through and we can use things like a QQ plot, which you can see there with the blue dots. We can use frequency histograms, and we can examine those patterns to see if there's evidence of any deviation from normality. For the QQ plot with the blue dots, the orientation of those dots should be pretty much a straight line. And so because we can see some kind of deviation from those dots in the upper right corner of that graph, we know that that's probably not a normally distributed data set. And maybe we need to think about what to deal with that. Similarly, with the histogram, you can see that it's pretty heavily right skewed. And so that also suggests that maybe it's not normal. We could also look at other things like residual plots, which we'll be doing in the future. And in some cases, there's even statistical tests, such as the Shapiro-Wilks, that you can use to test normality. So as you can see from the R code I entered on the right side, it's relatively simple to do. I just caution you about using these types of statistical tests to determine whether or not your data are normal, because usually if you are analyzing a very, very large data set, you're going to probably find a difference, even though your graphical means of evaluating normality don't detect anything different. And so there's kind of an issue that happens with statistical power. So remember, when you have lots and lots of samples, you're more likely to find an effect. And so if you have a really large sample size, you might have a data set that graphically looks completely normal. But then when you analyze the Shapiro-Wilks test, you might say, hey, these are significantly non-normal, even though it probably isn't a big deal. So again, just kind of be cautious with those tests. With homogeneous variance, we want our variances to be approximately equal, so homogeneous across the different groups. And so one of the easiest ways, I think, to evaluate this is to simply use a box plot, like you see in the bottom right corner. Box plots are helpful for kind of getting an idea of how variable our data are across those different groups. And so in this case, they're relatively equal. There might be a little bit of unequalness with the red and blue being a little bit smaller than the green in this example. And so we might want to think about possibly applying a technique to deal with that, which we'll talk about, but not terrible. So we can use box plots for this. You can just simply look at the standard deviations and see, well, are they about the same? Do they seem about the same? Well, if they are, then they are probably homogeneous in their variance, about equal. And then keep in mind, just like the Shapiro-Wilks, know that there are options too to evaluate homogeneous variance, such as the F-test and Levine's test. So it's important to be extra cautious in a few situations. So while most tests are quite robust to issues of normality, and in some cases even the variance issues, if things are very, very non-normal, like they're very heavily skewed, or maybe they show a bimodal distribution, like two humps instead of one unimodal single hump, like in a normal distribution, then you might want to be cautious and think very carefully about how you can deal with that. If you have very large distributions across your two groups you're comparing, like you see in the upper right corner, like those distributions are almost mirror images. Well, if you're trying to compare those two, you might have some issues too, okay? And outliers, while they're not really an assumption, they are an essential thing to consider every time you do your analysis. Outliers are real data. You can't just throw them out, okay? You need to have a non-statistical reason to remove outliers. Okay, if you don't have a non-statistical reason, that might be, for example, a data entry error, it might be a methodological error, something that's not related to the actual data, then maybe you can remove them. But if you don't have one of those issues, leave them in. They're real data. And so if they're real data, even though they're inconvenient, you should think about maybe an approach that can help reduce their influence. So typically it's safer to ignore these issues, these violations from your assumptions, if you have a balanced design, if you have a pretty large sample size. So again, your sample size N is much bigger than 30. And if your groups seem to be relatively similar in their distribution. So maybe they're all skewed in the same way, but they're not highly skewed. Then you're probably fine to, in some cases, even accept that there's a little bit of violation of the assumptions and just rely on the robustness of your test to carry you through. So there are some solutions, though, that are useful to try. The main solution I recommend is to use transformations for your data set. So transformations are when you apply a mathematical formula to your data set in the same way. So say you have your response variable or your explanatory variable, and you apply like a log transformation to it. Okay, you're applying it to your whole data set. You're not applying it to different groups. Okay, so if you apply a log transformation to one of your response variables, you're applying it to the entire data set. Okay, not just one group. And natural log seems to be most common because it's really effective. Typically what it does is it helps normalize data that tends to be right skewed. So look in the upper right corner, you can see the red and blue curves maybe represent our data sets. And you can see those are pretty different. They're certainly skewed, they're not the same. But after we apply a log transformation, it normalizes them. And so now our data would meet the assumptions of the test. And now we would take the log transformed data and analyze it in the same way we would if it wasn't transformed. Okay? So again, just to highlight this, we are applying the same transformation to our variable, whatever it is, and then we're using that transformed variable in our analysis. Now, the downside of a log transformation is it doesn't work with anything less than a 0, so it'll just give you errors. And then if you do have zeros, as long as it's not a ton of zeros, what you can do is add an arbitrarily small number to it to allow yourself to use a log transformation. So we would phrase that as taking log of your variable x plus 1, or log of your variable x plus 0.001. And so say your x variable was number of cells or something, you're getting numbers that are in the tens of thousands, then maybe a log x plus 1 is appropriate. If your variable is small, you're getting 1, 2, 3, a half, you might want to do a smaller number like 0.001. You just want to do an arbitrarily small number that isn't going to hugely affect your data set. Okay, so just be cautious though. Nothing will fix zeros if you have a ton of zeros. There are other approaches, such as zero-inflated models for those, but they're kind of beyond the scope of the class. So just, again, be real cautious, and that's why it's so important to dig deep with your data set and think about how it works. A square root transformation is simply done in R as sqrt and then your variable. And I think it's a very useful technique. It's usually when things aren't quite as skewed as a log transformation. And it works well when you have zeros, and it doesn't work with anything less than a 0. And so, be cautious with that. If you have like a negative number, it wouldn't work with that because you can't take a square root of a negative number. A cube root is another option, so it's kind of a step up from the square root. If you have a lot more skew, maybe a cube root is appropriate. And then I just want to call attention to an arcsign transformation. And an arcsign was traditionally proposed for proportion data, so like percent data. So your proportions, it should be between 0 and 1. I'm not going to give you a blanket recommendation that this should be used every time. There's kind of a misconception that this is the transformation to use when you have percent data. But in reality, whatever transformation you use should be the one that's best for your data. It should help you normalize your data or make it more equal in the best way possible, reduce the influence of outliers in the best way possible. And there's not just any one transformation that's going to be the gold standard. Again, it depends on your data and what your graphs show, what your pre-analyses show. So keep in mind, again, just to really emphasize this, when you are applying a transformation, okay, you're applying it across the full variable, okay? You are applying it across the full response variable, or you're applying it across the full explanatory variable, depending on what kind of data you're dealing with. Obviously, you can't apply a mathematical operation to a categorical variable. It doesn't make sense. So you're doing this to number variables. And so let's say that we are doing like a correlation and we wanted to look at how temperature was related to growth. Okay, so two number variables, let's pretend. And we see that there's some kind of non-normality there. Well, we might apply a transformation first to our explanatory variable and then take a look at our graph to see if it's normalized. And if that doesn't work, then maybe we apply it to the response variable and take a look at our graph and see if it applies, and maybe it does or doesn't. And in some cases, we apply it to both. But again, you're applying it ideally in such a way that you're doing the minimum amount of change from your original data set as possible. So I wouldn't just transform things willy-nilly. Make sure you're doing it methodologically or purposefully. Okay, so real important, transformations don't always fix things, okay? Oftentimes they make it worse. And so you can have a situation where you apply a transformation and it does either nothing at all and will not fix it, or again, it will make it worse than when you started, okay? So you have to be cautious. And then watch out in R, because when you try to do things that result in nonsensical numbers, it will give you an error like an NaNs as your data. And so that itself, if you're not aware of what you're doing, you're not paying attention, you could then be going on to your next step trying to analyze that data. It's going to give you errors. It's going to mess everything up, okay? So again, always be thinking about what you're doing, what the resulting data set looks like before you run that analysis, okay? And generally speaking, you can pretty much use any transformation you want as long as you can back transform it and get the same values again, okay? So I'm giving you some ideas of what's common. There are many others out there, okay? So just be aware. And you can even see some examples of what log transformation has done. So in the top one, we've improved it. The middle one, yeah, it's improved it a little bit. And you can see the variances for the last one, the box plots, certainly has helped equalize those even more, okay? Now, extra important point. Okay, so circle this bottom line if you need to and star it. It is absolutely critical that you are making these decisions on your transformation based on how well they help you meet the assumptions, okay? You should not be looking at the p-value when you're doing this. You should be paying attention to the assumptions and ignoring the p-value, okay? Ideally, you apply transformations even before you do the analysis. That doesn't always happen, but you do not want to use the p-value to dictate which transformation to use, because that would be called a form of p-hacking. So where you're trying to artificially influence your results. So assumptions should be met. Your decisions on which transformations to help you meet those assumptions should be met without considering the p-value. One potential solution to dealing with violations of your assumptions would be to use what we call a non-parametric test. So parametric tests are those that we've been talking about so far, like t-tests, that we'll talk about in the future with ANOVAs and Pearson correlations, regressions, two-way ANOVAs. Those are all those tests that are reliant on assumptions of normality and, of course, homogeneous variances. But there are non-parametric equivalents out there. So equivalent tests that do not necessarily depend on normality assumption or homogeneous variance assumption. So there's a variety of non-parametric tests out there, like for one sample t-tests, pair t-tests, we have the signed rank and Wilcoxon signed rank test. With two sample t-tests, we have the Mann-Whitney, and one-way ANOVAs have Crisco-Wallace. Even two-way ANOVAs have things like Friedman tests. Pearson correlations have Spearman correlations. So it goes on, that there's often non-parametric equivalents. And they're non-parametric because they don't rely, again, on those normality assumption and sometimes they don't rely on the equal variances assumption. Now, let's keep in mind that an even better option is what we call generalized linear models. Now, those are interesting because they're a type of statistical analysis that lets you actually specify the distribution your data is in. So maybe your data is count data and it doesn't really follow a normal distribution very well. It's instead Poisson distributed. Well, you could use a generalized linear model to analyze that. Or if you have binomial data, let's say that you measured success or failure of something, or you measured, say, the yes or no's, or whatever. You have those kinds of binomial data sets and then a bunch of factors that affect them. Well, then a generalized linear model will be used for that and be very useful for, I think, understanding the intricacies of those data sets. It's a little bit beyond the scope of this class, but it's the next logical step that I'd encourage you to explore after you complete this class. So the violations of assumptions might point us to non-parametric tests. And before I just blindly say that you should use these non-parametric tests, I want to talk about their advantages and disadvantages. So for one, they tend to rank your data as a part of the analysis. So there are some good parts and bad parts about that. Now, the good parts is when you rank your data, it helps better deal with big extreme outliers. And so by ranking them, they no longer have that same magnitude of the effect, okay? And then another advantage is in some cases, you might want to use non-parametric because you're more interested in the medians than you are necessarily the means. So that might be another approach where non-parametric makes more sense. Now, the bad part, they're traditionally low power, okay, compared to their parametric equivalents. So you could have a situation where your two-sample t-test shows you a significant effect, but then you go to do your non-parametric Mann-Whitney u-test, and it doesn't find a significant effect. And so in some cases, non-parametric tests can have lower ability to find those differences, even though they might be true. So be cautious about that. And really important that a lot of people don't realize, a lot of these non-parametric tests actually do still have assumptions. They have, of course, the assumption of independence, random sampling, something that's kind of always implicit in there, but something to always remember ourselves as scientists. Some of them, like Wilcoxon signed ranks test, assumes the distributions are actually symmetric. They may be not normal, but they should be symmetric. Mann-Whitney assumes the two distributions should be about the same in their variance and about to have the same kind of skew if they are skewed. And so that is not too far off from being normal and having equal variance right here already. So you can tell that a lot of these tests actually do have some assumptions, and it's kind of important to dig into them a little bit if you go to apply them for your own data set. So always keep that in mind. So in my opinion, and this is my opinion, of course, you're going to have to make your own decisions as a biologist in the future on the right approach. But in my opinion, use these kind of as a last resort. So when you simply cannot transform to make it work, when your sample size is small, or you have tons of outliers, or maybe you want to know how the differences in medians might be, sure, go ahead and use them. But when you can more or less transform things to make it good enough, or you have a decent sample size, you don't have a big outlier issue, then go ahead and use the parametric tests and just rely on the robustness that they provide. So again, I want to highlight finally that there are better options. So in the future, I wanted to guide you towards learning about permutation tests, or what we call resampling and randomization tests, which are really cool new approaches to data, where you essentially shuffle up your data randomly into your groups and then repeat this many times to create your null distribution. Okay, so instead of relying on like a t distribution, you create your own probability distribution based on your own data set. Then you compare your data, your raw data, the original one, not shuffled up, and see how it would then compare to those. that were all shuffled up and forming that null distribution. So kind of a really cool approach. You can read about that in chapter 19 if you'd like. Generalized linear models, which you mentioned before, and also something else called generalized additive models. Again, really useful when you want to specify the distribution you're using. Or in the case of generalized additive models, when you have a situation where, well, maybe your data isn't necessarily linearly related, but maybe it has a different non-linear kind of relationship between variables, and you might want to go down that route. So it's kind of keep those in mind as maybe the next step of your education in the future. And you can read about both of those with the links I've provided below. Okay, with that, I just want to encourage you again to ask me if you have questions. We'll be using transformations pretty much throughout the whole semester now, because now we're going to need to make sure that we understand well if our particular analyses, our data that we're using for our analysis, violates their assumptions that they have for each particular test. And so you'll be applying these again and again and again. So really make sure you have a firm understanding of this. And of course, as always, let me know if you have questions.